Hi everyone. So today we are going to kind of deviate from proofs for a little bit, just to get some more background information on the logistics of mathematics. So we're going to start with some set theory. So you may have heard of sets before, and if you haven't heard of them formally, you have been using them. So whenever you write the z with this sort of double slash here, that is the set of integers. So you've kind of already been using sets without even knowing it. So to start off, we just have quite a few definitions to begin with, so that we can build the foundation to set theory here. So we're going to consider this to be the beginning of chapter 8, so intro to set theory. So to start off, what is a set? So a set is a collection of objects or elements. So when we say something belongs to a set, sort of membership, we use this notation here, this sort of E with a curvy spine, I would say. So we would say A belongs to the set of A. So it is important to note in this formation here that elements are written in lowercase and sets are written in capital or uppercase. So if I'm referring to an element or an object from a set, I'll give it a lowercase letter. If I'm referring to the whole set, I'll give it an uppercase letter. So this phrase here, A with this curvy E, means A is an element of or a member of set A. If I want to say something does not belong to a set, then similar to inequality, we can just put sort of a slash through it, and we can say A is not an element of A. So looking at here, we can say, let's define a set. So if I want to define my own set, there are some sets that are just mathematically accepted worldwide, but you can create your own. So if I want to create the set A here, we can say A is equal to, and then to kind of list out the ideas here, we put a curly bracket, and we put X, and then a colon, and we define what X is. So X is a student at North Star. And then a curly bracket. So if I want to define A to be the set of all students at North Star, then this is how I would do it. I would say A is equal to X, where X is a student at North Star Academy. So looking at mathematically accepted ideas, we have the universal set, meaning the set that contains everything. So that means for all X, whatever X is, it belongs to the universal set. So U has everything in it. The empty set, as you can sort of infer, this is also called the null set. Most times you'll hear null sets. And that is described as 0 with a slash through it, it means that nothing belongs there. It's empty. There's no elements, nothing belongs to it. It is a completely empty set. So that means for all x, x does not belong to the null set. So this is some sort of just everything is in U, but nothing is in the null set. So these two are the extremes of mathematics, where everything belongs to the universal set, where nothing belongs to the null set. So next we can sort of define the sets of explicit values. So when we look at different types of numbers, we kind of have this sort of scaffolding structure of numbers. So mainly we're going to focus on real numbers. And so we know that there are sort of subsets of real numbers, and subsets is what's going to come into play here. So there's sort of this hierarchy going on. So if you've never really examined this, hopefully you have at some point in your mathematical lives. But we have 3 sort of categories of numbers, which are kind of like the Russian nesting dolls. They all nest inside of each other. So if I had to start with sort of the smallest circle in this sort of hierarchy, these are the integers. So these are essentially whole numbers that do not have decimals or fractions or anything like that. Inside that, so sort of this nesting doll picture here, we have the set of rationals. So these are things like 1/3 or 2/3, where it's a rational number. It has either a pattern or it's the decimal stops at some point. And we'll write an explicit definition of rationals other than the loosely based one that I just defined. And then inside all of those is the set of real numbers, where it includes both the rationals and the irrationals. So the only thing that's really added to these two in the middle is just plus the irrationals. So those are the set of real numbers. And then if we had to go outside of this, we could put the set of complex numbers, but we're not going to go that far in this class just yet. So let's actually just go through and define these sets. So the set of all integers, so let's start with the sort of smaller set of those 3. You've been using this notation already. So this is z. So z with sort of this backslash cross through. And this is the set of all integers. So we can say this is equal to, and then curly brackets, dot, 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 -3, -2, -1, 0, 1, and then keep going on and on forever and ever in both directions. We can create subsets of integers so we can get more specific in where we're limiting the values. So if we want to say just the set of positive integers, we can use a notation for that as well. I will forever spell integers incorrectly. So the set of positive integers is just z, the same z, but then it kind of has this plus sign as sort of an exponent here. So this is everything from 1 and up. So you'll notice that 0 is not included here, and that's because 0 is not considered positive, nor is it considered negative. So 0 is not included here. And that's going to be something that's going to come in handy because there are going to be quite a few proofs down the line where it won't work for 0, but it will work for every other integer. So in order to define that, we might need to know some instances where 0 doesn't exist in that set. So, sort of if we want to include all of the positives and 0, then we have the set of non-negatives. Non-negative integers. So this is the z with a greater than or equal to 0. I know, not very original, but that is what we have. So this is from 0, 1, 2, 3, and so on. So this includes everything from 0 and above. Again, just the non-negatives. If we want to include the sets of non-zero, so maybe we want to include the negatives, but we don't want to include 0, then we have a notation for that as well, and that is z with an asterisk at the top. So just this kind of star shape above, and that is everything from negative infinity to positive infinity, excluding 0. So -2, -1, 1, 2, and so on, in both directions. And then from here, we can dive into some other sets. But these are the 4 biggest ones. So we have the set of just integers, the set of positive integers, the set of non-negative integers, and the set of non-zero integers. So once we move on to the rationals, the notation is going to look very similar in terms of positive, non-negative, non-zero, but the base letter will be different. So for the set of rationals, this will be defined as Q with sort of a line going through the middle of it here. And so this defined is written as A over B, where, let me move this down here so that it's clear. So we would say set A over B colon, where both A is an integer and B is an integer. So any number that can be written as A over B is considered a rational. And you can see that that also includes the set of integers, because I can just take an integer and put it over 1, which 1 is also an integer. So here we can see that sort of nesting doll picture going on. So the set of rationals is described as Q. So if I want to say simply just the positive rationals, the set of positive rationals, we would say that this is Q plus, and we would define that as A over B, where A is a member of Z plus and B is a member of Z plus. So both A and B are positive integers. We also have the non-negative rationals, where we have Q greater than or equal to 0. That is A over B, where you probably guessed it. A is a member of the non-negative integers, and B, however, is a member of the positive integers. So you may be looking at this and you may be thinking, wait a second, why aren't A and B both part of the greater than or equal to 0 set of integers? Well, if you think about it, if I only exclude A and B to be part of the non-negative rationals, then I'm missing out on this. Well, I'm not missing out. I'm defining an undefined number. So if I put b into the non-negatives, then I'm saying that b could be 0. And then that would be undefined. So I don't want to put numbers that are undefined in my set. So for most of these, well, for all of these actually, b is going to be part of the set of integers, positive integers, so that we don't have a division by 0. So now we can say the last set of rationals here, the non-zero rationals. And we define this as q with that asterisk above, and then that is going to be equal to a over b, where a is a member of the non-zero integers, and then b is a member of the positive integers. So again, we want to make sure that 0 is not included. However, we don't want to just say that b is also a non-zero rational, because then if we have division by 2 negatives, then essentially we would just be using the positive rationals. So here, that's why b is just defined as a positive integer. So moving on to the set of real numbers, we have a symbol for this. And this is R with kind of 2 spines, I would say. And this is just any value between negative infinity and positive infinity. So it's literally anything. So it can be pi, it can be e, it could be 2, 4, whatever you want it to be. That exists in the real set. So we want to use this if we are trying to prove anything works. You'll probably realize that that's almost impossible to prove anything for the whole set of reals, but sometimes it's useful, so we just have that here. So again, to just define the subsets of the reals here, we have the positive reals, where we have r plus, and so this is defined as x, and I haven't explicitly said this, but this colon here can be read as such that, so x such that x is between 0 and, or excuse me, not equal to, between 0 and infinity. And then the non-negative we have as r greater than or equal to 0 is equal to the set of x such that x is between 0 inclusively and infinity. And then lastly, we have the non-zero set of non-zero reals, where, again, we have this asterisk here, where that is x such that x is between 0 and infinity, but we can define this as the absolute value of x. Another way that you could probably do this is with a union, so we could say negative infinity to, say, well, I have to use an interval here, so I can use negative infinity x 0 union with something like that. That'll work. So regardless, it just means, again, 0 is not included. So from here, we can continue with some more definitions, and a lot of these are going to follow directly from logic, like our symbolic logic that we use in the beginning of quarter 4, but using them in terms of sets. So to get some, again, some more definitions, this day will just be full of definitions. We have 3 that we want to focus on, and that is going to be complement, intersection, and union. So if you take stats with me, these 3 terms hopefully are familiar to you. If you do not take stats with me, these are going to follow directly from symbolic logic, just a little bit of a more curvy attribute to the symbols. So definitions here, we have suppose U is the universal sets, and A and B are sets. So the first one here, the complement of A, and that is denoted with A prime, is the set of all elements not in A. So then when we would write this with our set notation, so A prime is equal to the sets of X such that X is not a member of A. So the second definition we have is intersection. So the intersection of A and B, which is denoted by A with an upside down UB. I'm kind of made that very wide and drastic, but just so that we're clear, this is curved. This is not the and that we are used to seeing in logic. So this is the same principle. Intersection means and, but we use this curved symbol when we are intersecting sets. So this is the set of all elements that are in both A and B. So essentially here, if we have A intersect B, we have X such that both X is in A and X is in B. And then our last definition we have is union. So the union of A and B, which is denoted with AUB. Hopefully union is familiar to you in this notation, this way that we did down here. So that hopefully does not look foreign to you. So this is the set of all elements that are in either A or B. So we can denote that as A union B is equal to X, such that X, let's say, are either. So either X is in A or X is in B. So we have, or both. So that's another caveat here. So union, it could be in A, it could be in B, it could be in both. So that follows the set or the notion of or from logic. So it could be in both. This isn't an exclusive or situation. So to kind of put these in terms of Venn diagrams, again, if you're in my stats class, this might look familiar to you. So if I have the box here, this is the universal set. So I'm going to put U out here. And A is inside that set. So this is set A. A complement is everything that is not in A. So that shaded region here. If I, again, have the universal set and I have A and B, and this is A intersect B, well, that's everything that's in A and B, so just this middle region here. And then again, if I have the universal set and I have A and B, and I'm saying A union B, well, again, from my definition, that is everything that's in A or everything that's in B, or both. So that's essentially going to be all of A and all of B. So these two whole regions shaded here. All right, so we're going to pause for today, and next week we're going to pick up with intersecting and unioning different sets of reals or rationals, and we're going to sort of get their definitions in. So, for example, one quick hit preview, I would say, if A is equal to the set of non-negative integers and B is equal to the set of positive rationals, if I have A union B, so I have the set of non-zero integers union with the set of rationals here, positive rationals, then that is going to be the set of non-negative rationals. However, if I have A intersect B, so I have the non-negative integers intersect with the positive rationals, then that is going to be equal to the set of positive integers. So we're going to do a lot more with this next week. So just giving you a preview of what is to come. All right, so please fill out the Google form for today. And if anybody has any questions on any of this, I will have office hours tomorrow. So I will be logged on from 1 to 1:30 for office hours tomorrow. So log on to Zoom if you have any questions. If not, have a great weekend.